Okay, welcome to session 2 of our ML model building lecture. Today we left off on Python basics, so we're going to touch on just a little bit of Python basics. We're going to go through data types, data structures, and some of the foundations that we need, ending with pandas data frames, some of the foundations we need to build these models. And then we're going to dive into models. What are they? Linear regression, and touch on some modeling methodology at the end if we happen to have time. Okay. That did not go to the right screen. One moment. I apologize. Let me actually share this other screen.
Where do you post the recordings?
I will send a link to that. That should be in the StreamYard. And I believe they get posted to YouTube as well. Let's do... All right, what do you guys see here? Yep, that looks right. Okay. We will switch to just this view here. So Python basics. In the Python course, we left off on variable. If you guys recall from the Python basics course, we have different variable types that we can work with in Python. So we have numeric variables that can be represented as either integers or floats. We have dictionaries, which are key value pair lookups of objects, or key value pair lookups of entries into this object that can be contained with an object. If you think of a JSON payload can be a dictionary object. We have Booleans, we have true false values, which we can use in machine learning. Booleans are really important, by the way, because they represent zeros and ones in our supervised learning paradigm. So in supervised learning, if we have some apples, bananas, pears, and we're trying to say, is this an apple, yes or no, across all these pictures of fruits, you can either represent that as yes or no, or you can represent yes and no as 1 and 0, or you can represent yes and no as Booleans. So everything gets kind of converted to these Booleans under the hood in machine learning. We have sets and we have sequence types. So we have our strings, our tuples, and our lists, things that we can iterate over. We can say for value in string, print out each character in the string. For value in tuple, print out each item in the tuple. Over a list of attributes, print out those attributes. Let me see. I'm trying to decide if we hop back and forth. So we'll do a quick overview. We'll add a few concepts here and then we'll jump into, I have a notebook for this. So we also talked about control structures. So in addition to data types, Python and programming languages in general also have control structures that controls where the execution of the code is happening at any point in the code. In Python, the ones that you need to be most familiar with as a precursor for this course are loops, are for loops. We don't use a substantial amount of while loops. I think everything in this course you can do without a while loop. So for loops particularly, and conditional statements, if else statements, if else, elif, nested if statements. Being familiar with break and continue and pass will help you, but I think for this course it's really just sufficient to be familiar with for loops and conditional elif statements. So if you're feeling pretty good about that, I think you're in a good spot. In terms of data structures for this course, we're definitely going to focus on lists. We use quite a bit of lists and dictionaries. I don't think you might be able to get away without tuples. And don't worry about these user-defined ones here. We will use quite a few functions, though. I think your first assignment actually has a function in it that you are supposed to edit and get it to return the right value. I think part 3 of assignment 1. So Python, I wanted to remind you guys on how Python functions work. Inside of a Python function, when we want to create a function, when we want to declare a function, we have to set it up in a particular way. We have to structure it in a way that tells Python, this is a function that I am going to create and define. And the way that we do that is with a def keyword, DEF. So we use this DEF keyword, and it tells Python, hey, I'm about to send you some information that is a function. After that, we have to name the function. So here we create the name of the function. In this case, we called it add. And this is the way that you reference that function later in your code. So if you want to use the function later, the way that you call that function is by calling the function name. To that function, we have to pass, we have the option of passing arguments and parameters. So we can pass X and Y in this case. We're adding 2 numbers here. The syntax to tell Python that you are done with the first part, the declaration, the definition and declaration, or the function definition here, is to end it with these 2, this colon here, to end with this colon. And that tells Python, I'm done naming my function and I'm done passing arguments. This indented section is the body of the function. If you recall, Python is totally space-based. It's an indentation-based language. And so this indentation here tells Python that this is the body of the function, all the code that is to be executed within the function. If we pushed this indentation back, then we would now be outside of the body of the function. We would be outside of the function. So inside of this function so that's the function code, that's number 5. Inside of this function, we have this first line here that says print f arguments X and Y. So we're printing and we're doing an F print, a format print, which is going to make anything inside of curly braces executable code. So we're saying print, and as actual output, we're saying arguments are, and then we're printing the value of X. And then we said and we're printing the value of Y. And then we're returning to the function call X plus Y. So we're adding X and Y together. That will execute first. The output of that is what gets returned to the return statement, and the return statement passes that value to the function call. Whenever you call add, it receives back X plus Y. This is the return statement of the code. So every time you call this function, that is what gets returned back. Okay, I am going to pause here for just a moment. Any questions so far on Python, on data types, control flow, and functions? Okay, let's look at some code. Let's go to so inside of the student folder, you guys will actually be able to to find a couple of notebooks here. One is this Introduction to Python notebook. And I've got, this describes that Python is kind of more of a higher level interpreted language compared to some of these lower level languages that are closer to the machine. And in here, let's start to look at some of these things. So here are all our data types in Python. We have examples here of numbers, strings, lists, dictionaries, tuples, fields, file sets, Boolean, and the none type. So here we have numbers. We have different types in Python. So we have the number 1, 2, 3, 4. That is in fact an int. We have the number 3.1415. That is in fact a float. So anything with decimal points will be a float. We can skip some of these. Python lists are very interesting because you can have different data types within the same list. So here we have an integer, which is a 1, an integer, which is a 2. We have a string representing 3, and this is actually a list here, a list. So we have a list inside of a list, and then we have a float, 4.5. We can see that, what do you guys think the length of this list is? It's kind of hard to tell. Oh, sorry. What do you think how many values do you think is in this list?
3.
Yeah, there's 3 values. So even though we can see 1, 2, 3, 4, there's in fact 3 because this is the data type of, let's put this into a variable. Okay, and if we did type of my list at 2, remember Python is a 0-based index, so the positional index of the thing at location 2 is actually 1, is actually a list. So this is it counts this as a 1 object because it is a list. We can use Python's range function if we want to iterate, generate a series of 10 numbers. Here we have a dictionary. This is a key value pair. Sorry about that. There we are. We have food is spam and taste is yum. We can see that that is a dictionary. We'll skip tuples here, file sets, Boolean. If this is what I was saying earlier, ones are represented as true. So if we cast a 1 to the data type Boolean, remember casting is when you pass in one value and you want to turn it into a different data type, a different data structure. And actually anything gets cast to true except 0. We can use Booleans are what gets returned from equality operators. So if we say 5 is equal to 6, that returns false. If we say this is equal to that, that returns false. If we say this is equal to this, we actually get true. None is a special type in Python that we will use quite a bit. So if we set the variable this is equal to none and we print out the type of this, we get none type. So the none type variable is equivalent to null. If you're familiar with null from your SQL course, this is the null data type for Python. It's called none. It's what we use to represent when there is no information. There are different ways that you can print to the console. Here we can just call print hello world. We can print a variable. We can store a string into a variable and we can print that string. We can do an f print, which we've seen, format print, which we've seen quite a bit. This is where you put an f in front of that string statement, and then anything inside of curly braces is executable code. There are 2 types of comments in Python. We have single line comments and multi-line comments. Single line comments are created with just a single hashtag and only execute for one line. So you have to put a hashtag for every line you want to comment. The multi-line comments are opened and closed by 3 ticks. So you 3 ticks to open it, 3 ticks to close it. And as long as everything between these 2 sets of 3 ticks are comments and are not sent to the interpreter. So this information is not sent to the interpreter on the machine. It is not actually executed as part of your code. These comments are just to help us as humans understand what the code is doing, and explain to your friends and your coworkers and your colleagues what's happening within the code. Some types of variable assignment are illegal. You guys will probably get errors if you try to do things such as this: $, stars, exclamation points, and reserved keywords. You cannot change the value of the number 3, for example. You cannot change the value of integers and numbers within Python. We can assign things to parameters, but you can't change the value. When you set up an equation, just like in math, everything should be on the right side of the equation. Then you assign that to a value. This, for example, is illegal. You can't add a plus b and then assign it the value of 3. There are numerical operations. I might skip over some of this. You guys can play with some of these. Incrementing, decrementing. Remember, you can use the plus equals operator, the minus equals operator. Take things to the power with the star operator. Casting, this is what we were mentioning earlier. You can change the data type of something in Python. So if we have a float, my float, I want to cast it to an int. We have 36.3. We can call int and then open parentheses, pass in what you are trying to cast, close parentheses, and now 36.3 gets converted to 36. Python has a built-in math library. You can import it by calling import math, and it has things such as math.py, math.square root, and you can use these for some simple mathematical operations instead of building a square root function yourself. Python also has a library called random. You can import random, and you can use it to generate random numbers for you. We will probably use this quite a bit. You might even be in your first assignment. This random package is quite useful when we're trying to generate random numbers for machine learning algorithms and problems. We'll use the random quite a bit. Random.choice is another useful function where you can pass it a series of options, and you can say random.choice, pick one. And you can use this like heads and tails. You know, maybe we have a coin, and we want it to pick either heads or tails. I think this will work. And I did not import random. Moment. Oh. And some of the time it'll pick heads, some of the time it'll pick tails. And we could actually create an experiment and say, run this 1,000 times. And this is essentially a simulation of somebody flipping a coin, flipping heads and tails. So we can use these random number functions to create simulations that simulate things in the real world, so we can test those out before implementation. String operations, we'll skip over these. Concatenation, list operations. There are some conditional statements in here. If you guys So if statements, if you guys need some extra practice, some quick reminders, I would encourage you to look at if statements, the if else statements here, try to understand what's going on. And or not for, we won't use a ton of while loops. There's some work with functions here. This is showing that indented space matters. This is going to give you an error. And we won't use a lot of keyboard input here. Any questions so far on just general Python? This is, let's say, everything in this notebook. If you're feeling pretty good about this, you're in a really good spot, and this is everything you need that we're going to build off of using packages such as pandas and sklearn.
I put a small thing in the chat, but I don't think it's like something that relates to this so much. I was just curious about how you could do random but suppress the last value.
What do you mean by suppress the last value?
So like, I guess you know, the idea like true center and then like optical center. So like sometimes you want random, but sometimes random doesn't feel random because random sometimes has this, like, it's not like, so if you have, instead of heads, tails, if you had more like 4 options or 5 options, but you never wanted the next roll to be the same as the one that came previously. Does that make sense?
Oh.
So you need some sort of a way to store temporarily whatever the last roll was, and then ensure that that can't be the value. So essentially, it would just be probably. I think I'm answering my question maybe, but you'd have to like sort of say like, if it's the same as the previous roll, try again and don't print it until you get something that isn't.
Yep, random, but not previous roll. Random. We could do.
Yeah, there you go. That's a good one.
Okay, so we have this random choice list, and that's going to be 1, 2, 3, 4, 5, 6. Oh, I forgot my number 3. 3, 4, 5, 6. Okay, and then we're going to say last roll was 0. We need to define that out. Let me see. Okay, I'm going to change this later. I just have to think about it. Is null, is none. And okay, so now we're going to no, that's not what we want to do. Because we need to keep track of it, and are we keeping track of it in the function? We'll just take in last roll. And random choice list. We're going to move this outside of the function. Last roll equals none for number of rolls equals 50. 4 rolls. Oh, I forgot. For roll in number of rolls Yeah, class roll. No, that's not what I want to do. For roll in number of rolls. If last roll is
Would it just be if last roll is random choice? Or
random choice, remove last roll. So we're just removing the last roll and then we're resetting last roll here. I don't think we're even calling. Yeah, I didn't even need this function. There we go. We didn't even need a function. Okay, I think this will int object. Oh, range. Oh, that was my worry that it removes it each time. I just want to remove a value from a list. It's going to be else random choice. Sorry. Random choice list. All right, there's a error in this. I think I know what it is, but I'm not going to fix it right now. Try to fix the fun exercise here. Extra practice. Try to fix this code so that it works. All right, I sent that in the chat. Fun exercise. It's I think I know what the issue is, but I'm gonna let you guys try to play with that. Other questions on Python? Okay. We're going to keep going for another 20 minutes and then we'll maybe take a break here. I do want to get to I do want to get to oh, and actually I have a breakout activity for you guys too. Actually I have two in here. But I do want to get to pandas. Okay, let's. In this class and through assignment 1, you're going to start to become really familiar with it. You guys are going to be working with pandas. Sorry, actually, I'm going to go into presenter mode here. You guys are going to be working with pandas, and pandas has there we go. Trying to figure out, there we are. Okay, pandas is a library that we use, which looks and feels maybe similar to Excel, might be a good analogy. So instead of just saying straight text of, this is a standard Python formatting. Okay, so here's a good description. This is a standard Python formatting, and we see the index here, and we just get straight text output of these data values. And so the index is over here on the left. The data is right here. The column label is down here at the bottom and it says temp. And the data type is over here and it says float 64. When we leverage the data frame object, it actually takes these columns and formats them into this type of format. So you can see how much more friendly this is to read and to work with, especially if you're working with a lot of data or you're working with this data very frequently, or there's a lot of columns or it's a substantial amount of rows. So here's the standard Python format for what that data might have looked like before. And then the pandas package formats the output in this way. So this is one of the things that a lot of people like about the pandas package, is it's just a very readable, friendly output where we can parse these columns and get to the information we're looking for rather quickly. The other substantial value that comes with using pandas is all of the built-in functions, tools, utilities that comes with it. So in pandas, we can load data from CSV and Excel very easily. We can make manipulations on these data frames. We can create visualizations very easily. So would very much recommend that you dive in and start working with the pandas packages, or the pandas package. Oh, I went the wrong way. I do have a cheat sheet here for you that can be helpful as you get started. It's kind of hard to see here, but I'll share these slides, and they're in the Google Drive. And if you go click this link, it'll take you to this cheat sheet. But if you want some quick, easy ways to remember all the functions for reshaping data, for iteration, for handling missing data, for indexing into the data, grabbing rows or column values, duplicating data, grouping data, etc. I've personally found this very helpful as I got started with pandas, just having something to quick reference. You can print it out, look at it as you're writing the code, and have just a quick lookup reference for functions when you're trying to do stuff. Okay, I think that is it. This was a reminder for myself to ask you all, were you all able to submit? We're going to look at some code here too, but were you all able to submit assignment 0? Okay, I just wanted to check. Perfect, great. So let's look at an example of some of these packages. Let's put some teeth on this. We're going to look at reading from data sources in Python. In this class, I'll try to always either give you the data source or have it be a built-in data source that we're working with. However, in the real world, you're going to have to get your data to the code. Your data is going to have to come into your notebook somehow. And your data could be in a bunch of different formats. Maybe you have a CSV file, maybe you have an Excel file, a pickle file, a JSON, or maybe more likely you have a SQL database you're trying to read from. There, if you click any of these links, it'll take you to the documentation for how to use these functions on the pandas data frame. And I would highly encourage that you guys get familiar with parsing through this documentation and reading this, because these functions and utilities evolve over time, and being able to read and understand how to use each function just based off of the documentation is a very powerful skill set. So we're going to import this. We're going to import the pandas package. Pandas has kind of a nomenclature of calling it PD. There's another package called NumPy, which is sometimes used by pandas, so we're going to import that as well. Pandas is used quite a bit as you're starting to become familiar with machine learning and data science. And then as you evolve and want to do more mathematically efficient operations, and you want to do things like build neural networks, for example, you're going to start to use NumPy more and more. But pandas is what we're going to use for this class. It's a really good place to start. NumPy is kind of optimized for linear algebra operations and leans better towards highly computational algorithms that need a lot of high computational efficiency. Okay, so we're going to import that. There are quite a few resources in here for you guys. Like I said, I want to try to give you a bunch of different resources to reference. So we won't be able to talk a ton about reading from data sources, but I think this is a good additional supplemental resource for how to read from data sources. Here we're going to load our, I'm going to have to. Here we have some house prices from Kaggle, that Kaggle website that I've talked to you guys about. There is a data set on here called the housing prices. I think we'll actually work with this data set. And so we're going to go and, I'd actually have to sign in here. But what you'll do is you would sign in and you would download this, and then don't forget to upload this to this section of your notebook here. And this will actually not work when I run it, so I'm not going to run these. But here is an example of using the read CSV function. So you're going to call pd.readcsv, the location of the file name that you want to read. In this case, if we just drop it at the highest level of this directory, it's in a local place where we can just reference it with just the raw name of the file. And then how do I want it to handle NA values? In this case, I'm telling it to convert NA values to a string value of NA. And we can run df.head, and we can see the output of this data frame. So df.head, pd.readcsv, when this cell executes, it returns a pandas data frame into this df object. So this df object, sometimes abbreviated df for data frame, is actually a pandas data frame. And now we have a bunch of tools at our disposal because we put it into this data type of data frame. Remember, in Python, we learned about data types, and you had integers and you had strings. Data frame is its own data type. It's an entirely new data type supported by this pandas package. And this pandas data frame comes with a lot of functions that we can call on it. So now we can call df.head, we can call .head on our data frame object, and it gives us the first 5 rows of the data frame and all of the columns. It's a really quick and easy way to do a visual sanity check and say, yep, this loaded incorrectly. This looks good. We can also call df.columns. There's a columns function on the pandas data frame, and that'll give us all the column names. Excuse me, I had to sneeze. We can call df.dtypes, and that'll give us all the data types. Are they integers, floats, objects associated with each column? I find this one particularly useful. We can call df.describe, and it actually gives us the row count, the average value, the mean, the standard deviation, the minimum, all 4 quartiles, and the maximum value of, 3 quartiles here, and the maximum value of that column. So we can kind of do a sanity check here. If we're looking at houses and we're looking at lot area, we can do a sanity check. If we saw the minimum value was 1, we might be suspicious and think that perhaps there were some data quality issues within our data. So this can, looking at your average value, your minimum, your maximum, your various quartiles, can help give you a more in-depth understanding of your data. To look at it in a more consumable way, we can actually call this on one column. With Pandas data frame, the way that you access a column is by a open square parentheses, that string value name of that column, and you close the parentheses. So if we want to see df.lot area. Oh, that's right. I have to actually run this code, so that's not going to work. But That's the syntax that you could use to do that. df.shape is a really useful function that just gives us the number of rows and the number of columns. So we can see that there are 1,460 houses in this data set, and there are 81 columns. We can split into X and Y here. If we want to train a model, we can say our target variable is the sales price variable, and we can split into, we can do df at label is equal to our Y. You will see this syntax quite a bit, which is why I have this here. In machine learning, we split into X's and Y's, which I'll explain in the lecture today what that is, but X is what we train our model on, and Y is what we evaluate our model on. And this X here, we can do df.drop, and we can drop that label because we don't want to give answers to our model in our training data set. And now we have our X and Y. I think this is good. I don't want to get too far into train test split. But this notebook is here. Feel free to open this and play with this. The other thing I want to touch maybe very lightly on and let you know for awareness perspective that it is here. We're not going to talk a lot about visualizations in this class, but if you would like some work playing with visualizations on common data science data sets, by the way, I try to give you kind of the really common data sets used as you're starting to get into data science. So here we have the iris data set, which is a measurement of flowers, and we're trying to predict based on their sepal width, their sepal length, their petal length, and their petal width, what type of flower it is. And so in Python, I'm gonna scroll down, you can make visualizations here in the code. I just wanted to show this, that there are easy functions that you can use to plot and visualize your code. And I think I actually asked you to do some of this stuff in one of your assignments, either the first one or the second one. So this can maybe be a reference notebook for you here, letting you guys know for awareness that that's there. Let's do a quick breakout activity. Did we do this one in the Python course? Maybe we did. We're gonna do it again. I'm gonna send this to you guys. Let's do a quick breakout activity here. I'll stop sharing my screen. Copy link. Okay, download this notebook. And move it to your drive location and see if you guys can work through some of the exercises on that. I'm going to combine the breakout notebook section with an actual break. So we're going to take a little bit longer break. So let's do, I'm going to say let's come back at 1:15. So it's going to feel like a long break, but I also want to give you guys some time to, we'll check in at 1:15. On break / breakout notebook. All right, we'll see you guys in a minute.
How's the weather over there in Omaha?
I think you're muted, Emily.
Oh man, thank you. I was talking. Gene, I just sent you access, and you as well, Josh and Christelle. It's the email address that you used with ODSA. So try again and let me know if you guys are still having trouble. And I dropped the link again. Weather in Omaha is awesome. I left Portland just in time because it's actually supposed to snow there this weekend. And here in Omaha, I think it's supposed to be up to 60 degrees on Sunday. Is that right? Maybe 70. Let's see. Omaha Sunday weather. It's supposed to be nice. I might go to the zoo. Oh no, not that nice. It's 46. I just got pretty excited. 46 is decent though.
Yeah, I live in a very predominant like Mexican neighborhood, and 45, and you can just smell the grills
Oh,
going. You can smell the carne asada, the onions. Oh my god, I love it. It's so awesome. It's a really nice neighborhood, not too much crime. You know, in Chicago you're gonna get it anywhere, but you know, very friendly. Everyone walking around, and the neighbors cook out. They bring us some stuff sometimes, so it's cool.
oh, that sounds incredible. That sounds really good, actually. Okay, perfect, Christelle. Glad to hear that. Were you guys able to? And I'm sorry if you guys were in the Python course because this might have been the same breakout, but perhaps it was a good refresher. Were you able to get this to print out? The trouble with tribbles is that they eat too many MREs. Oh, this is one. Oh, this one already has the answer. Sorry. Were you able to do this one? Let me take that out. 1 second. Okay. Were you able to do this one? Store the phrase in part 1 into a variable, and then use that variable to print this 20 times. How would we do that? This should be what the output should be like.
I just did the, phrase equals and then put the phrase in quotes and print phrase times 20.
This darn AI code gives it to a little too fast, but this code section here is going to times 20 is a really useful utility in Python that we can just hit times 20 on a string and it'll just duplicate that many times. This section here is going to say slice this backwards. So this is going to reverse the string essentially. If we say take everything starting at position 0 going all the way to the end of the string. Remember, if we don't put anything here, it just defaults to everything. And then this is our like how we move positionally, and -1 is going to tell us to move backwards. So it's actually going to give us the reverse of the string. Okay, take that out of there. What about this flow control one? Maybe this is.
I couldn't figure out what was being asked on that one.
Yeah,
It just seemed like it worked.
I think what happened here, now that I'm looking at this, I apologize, is just like I'm working with you guys in here now, I think I did that with the last sections class, and I didn't delete my code, so I actually think this is not, that's why I downloaded this at the beginning. I think this is not the right notebook, so I apologize. A simple tool. Did you guys get to use this, do this one at all? It doesn't have the code in it. I need to put a to-do ones. Okay. So enter the first number, enter the second number, enter an operator, and then print the output of that by taking 3 number, operator, number. So were you guys able to make a program that applied first number, operator, second number?
Do you want us to chat our answers, Emily?
Yeah, that would be awesome.
Okay.
And I will look both on Slack chat or private chat, either one. Okay, perfect. Let's look at this. Thank you, Luke. First number, second number, operator, got it. Let's get this print statement up here. Perfect. First number, operator, second number. So we're telling it what we're doing. We're printing the first number, we're printing the operator, we're printing the second number, we're printing the equal sign, and then we're running eval on, oh, that's a clever way to do that, on first number, operator, second number. I wouldn't have thought to do it that way. Yeah, that is, so 1, 2, slash 1 divided by 2. 0.5. That, yeah, that's perfect. Very clever. It's a really good approach. Okay, take that out since this is the answers notebook. And I think we're not going to do extra flashing sign, but last one is the advanced tool. So in this one, update your program to allow exponents, modular division, and integer division. I think we're going to be able to do that. That's why I thought your approach was clever. Let me just copy. Yeah, there we go. Thank you. Perfect. That's why I thought your approach was clever here, because if we had just wrote a bunch of if-else statements, which is probably how I would have done it, honestly, that said, if it's, modulo, do this, or if it's a division, do this, if it's multiplication, do this, we would have to add quite a bit of new code every time we wanted to add more functionality. So we're adding more functionality to our application. But in this case, we don't have to add new functionality. This is something that I would call generalized code. So it's generalized and it works. It works well. We don't have to update the code to add this new functionality. So it's really well thought out. And I think this is a really good example that emphasizes a programming concept, which is that more code is not better. You're actually a more sophisticated, maybe perhaps more experienced developer if you can write your program with shorter lines of code. So the less code, the more condensed. It's easier to debug. It's easier to add functionality to. So bigger programs don't necessarily mean more complex or higher quality code. And this is a good example of that. It's just one line of code, but it's extensible to both of these things. So that's really cool. I'm going to save that for the future. Okay. I apologize for that first one not having a bug in it. That's supposed to have a bug in it. I'll fix that. Let's move on and let's talk about, so that's great, guys. Let's talk about, let's talk about models. Finally, to the machine learning part of things. All right, so here we are. We're going to talk about some models. Just move my screens around here. Let's see what this is presenting from. It's presenting from the same. Okay, there is a fairly famous quote in the realm of machine learning from this individual called George Box, and I linked the Wikipedia article. Very, very, very intelligent individual. And he came up with a powerful quote that's really still substantially used today, which is that all models are wrong, but some are useful. So every model that we build is an oversimplification of reality. And for that reason, they will all be wrong. All models are wrong. None of them are incorrect. But sometimes we create a model and it's useful and there is utility in it. So I want to start with this as the foundation for how do we understand what models are. And models are, there is so much going on in the world. And let's say we want to, the theory is that if we want to predict something, if we want to predict an outcome, if we had enough data, we could predict that outcome. If we knew every single thing that happened at every single second in time, and I had all the data from all over the world and I was able to observe everything and put it into a supercomputer, perhaps I could predict every action you would do, everything you would do in your entire life. That's kind of the theory. But we don't have all of that data in order to make the predictions that we want to do. So what we have to do is simplify that to a smaller set of features, a smaller set of variables, a smaller set of assumptions. And when you simplify something, when we don't have all the information to make that predictive outcome, we're going to lose out on some performance because it's an oversimplification. It's an oversimplified model of something. And that's what our models are. Our machine learning models, our large language models, our AI models are oversimplifications based on a smaller subset of data available to us because we don't have the data of every single thing that's happening at every single point in time and every second right now. So just grounding in the fact that all of these models are incorrect. When we are training these models and we're making them represent something about the world, it's an incorrect representation. However, sometimes we can use that generalized representation to our advantage for outcomes. So let's move out of the theory and let's ground more in some examples here. A model is a machine learning or mathematical representation, a mathematical algorithm that maps input to output. It maps input, our input data, to an output prediction probability. So an output prediction or an output decision that typically has an associated probability with it. And it's based on patterns. It's the way that it makes this prediction is based on patterns that it learns from the data. So in this picture here, we have a, sorry, I'm trying to figure out where my cursor is. There it is. In this picture here, we have some input, and this, sorry, always messing with my screens here. This input here is, we have an apple and we have banana, maybe we have an orange, a banana, an apple, an orange, and we're giving it these labels. Does anybody know what type of machine learning it is if we have input data and we're giving the labels to the machine during this training phase? That's right, Jean. So Jean said supervised. This is supervised learning. So this is a supervised learning problem. We're giving this machine here in the middle input data, and then we're telling it, this is what an orange looks like. This is what an apple looks like. This is what a banana looks like. And over time, the model can start to build patterns. So this is called training, when we're giving it data with answers. And then the intent behind models, though, that we train is that in the future, we want to hand it data for which we don't have an answer. We want to hand it a new piece of data that doesn't have a label associated with it. And we want our machine to be able to assign a label to that. So the whole intent is, yes, we hand it labels in training, but during this other stage, which is called inference, during our inference stage, we want to hand it new input here, which is a picture of an orange, and we want the model to tell us what we should label this. We are handing it something and we want to know, we don't know what the answer is. We're asking the machine to tell us the answer, and it outputs orange. And this value orange has an associated probability with it, a probability that this is an orange. So when we say model, it's this mathematical representation. It's applying an algorithm in order for it to come to a conclusion that orange is the label that it should apply. So machine learning models, the thing to take away from this slide is that they map input data to output predictions. So when this is what we were going to be working with. When we had the X and Y in that notebook, the X is our input data here, and the Y are these output labels. We'll get there. What's the purpose of a model, right? Great, we have these machines and we can give them old information and old historical data and outcomes, mapped to outcomes, and then we can ask them on new data to make a prediction on that. But what's the point of that? Well, there are, we talked a little bit about predictive and prescriptive. So let's dive a little more into that. Predictive models can make predictions or inferences on unseen data. That's the key word here. You want your model to perform well on data that it's never seen before, unseen data. So our intent is to train our models to see and map their algorithm to be very efficient on historical data it's seen before. But the overall goal is not for it to perform well on historical data, not for it to perform well on data it's seen. We want it to perform well on future data. We want it to generalize to something called unseen data. So the whole intent is to use our model to predict future outcomes based on historical data. Let's think about house prices, for example. We have a house price that we are trying to predict, and we give it the history of house prices and what they've sold for in the past, features about a house, number of bedrooms, square footage in a house, how many bathrooms that house has, and what did that house sell for. So we have all these records, observations of houses, and we have features, columns about those houses. Our goal is not to get a model that trains really well on house prices historically and is good historically. That's maybe how we train it. But the ultimate goal is to have a model that can predict what a future house will sell for. So the ultimate goal is to have a model where I can hand it attributes about a house, the number of bedrooms, the square footage, etc., and it can predict based on those attributes what that house will sell for before it sells for that price. So we want it to be capable of predicting future outcomes. The reason I'm putting so much emphasis on this is because at the end of this, or at some point during this course, we'll touch on modeling methodology. And there are strategies that we're going to implement to make our models do something called generalize, to make our models perform well, not just on our training data set, but generalized to something called unseen data. So that's hence the strong emphasis on the unseen data. The other paradigm and you can do the same thing with sales, right? We don't want a model to be good at predicting past sales. We do, but ultimately it's a means to an end in order to create a model that predicts well on future sales. So there's utility to it. So that's the purpose of a model. That's why we have a model. There are also other types of models whose intent is to discover relationships between variables. When we get into clustering and unsupervised learning, some of the unsupervised learning techniques can be used to describe relationships between data, as opposed to predicting new outcomes. They're describing what relates these groups of people together in terms of customer segments. What does one group of customers have in common with each other compared to another? Okay, so let's talk about our first model. And our first model in this course is probably going to look really familiar to you, and maybe might make you hesitate that's actually a model, but it is here. We're going to use y equals mx plus b. So if you guys, recall when you were in, I don't know what course this would be, maybe high school algebra or something to that effect. Y equals mx plus b is how we define a line, something called a best fit line. So this line over here is our best fit line. The way that we create this line is y is our y-axis here. This y-axis is equal to m, the slope or the gradient, times x. So x is our x-axis here. So we take x, like the value 1, times some m value plus our intercept here, our y-intercept. So here's where our line starts, because remember, if x is equal to 0, x times, if x is equal to 0, 0 times anything is 0, 0 plus b is then going to be our intercept. So b is 1. And so our formula is y equals mx plus b, and m is going to be our rise over our run. So here we're going up 2 over 1. So m is 2. So y equals 2x plus 1 is our formula here. So y equals 2x plus 1 is the formula for this line. That is how we get this line. In the context, and we're going to start here with y equals mx plus b. It may seem an odd place to start, but I promise that this is important and that this is a foundation that is going to get us to neural networks. So believe it or not, this formula here, y equals mx plus b, is the foundation of neural networks. We're just going to take steps to get there. And I'm going to I really believe that it's just a nomenclature thing. It's just a terminology thing. So we're going to evolve this terminology. We're starting with y equals mx plus b for how to define a line. And then throughout this course, we're going to start changing this terminology. We're going to change it in this class, and we're going to start using different words for y equals mx plus b. But I want you to understand in your head that this is all the same thing, and we're going to build on this and get there. So this really is the foundations to neural networks. And by the way, neural networks are the foundations to large language models. So this is how we're going to get to OpenAI and ChatGPT. So input data. In machine learning, we call our columns, if you're thinking input data like an Excel sheet, we call our columns features. You've heard me say that multiple times. Now I'm formally going to, introduce this word features, and I'm probably going to, instead of saying column or attributes or variables or values, because those things are confusing and can be, those are overloaded terms that are used for multiple things. Oh, sorry about that. I'm now going to use the word features. So when I talk about the size of a house, the number of square footage in a house, that's a feature into a model. When I talk about the number of rooms, that's a feature into a model. So this is really just a nomenclature. I want to empower you with the tools to be able to search these things on the internet and then understand these and read about them. So in this case, y equals mx plus b, this m here is our feature. So if the outcome, y, is the price of the house, let's say for some reason we're buying houses and they vary between $0 and $6. M is the feature that we're working with, and X is the observation for that feature. So if you have a lot of houses, maybe one house has 2 bedrooms, a different house has 7 bedrooms. X is the value that you would replace there. So X would either be 1 for 1 bedroom or 7 for 7 bedrooms. M is the number that we are multiplying that by. So we're saying for every bedroom, if each bedroom is worth another $10,000, M would be 10,000. So it would be 10,000 times number of bedrooms. And from that, we can interpret that adding another bedroom will add $10,000 to your house in terms of that formula. Our output variable, this y variable here, is called our target variable. So from now on, I'll refer to y as our target variable. The target variable is what we are trying to predict. So you use features to predict a target variable. Really, we assign weights to a feature in this formula. We're assigning a weight or a value, such as $10,000, to a feature. And the combination of those things predicts the target variable. So in this case, house price is what we're trying to predict. The parameters, when I say parameters, these are the learned values. I'll either say parameters, weights, or coefficients. All of those things are the same thing. So the parameters, or the weights, or the coefficients, are the learned values that the model uses to make a prediction. M here is a parameter. So M is our parameter, weight or coefficient. So this is the weight that we learned. Our model learned that it was 10,000. Our model learned that to predict a good house price, it's 10,000 times the number of bedrooms that you have in your house. So that is the, B is also a parameter. This intercept is also a parameter. How do we think about B? Well, if you have a house that has no bedrooms in it, then 0 times M is just 0, and then we would have plus B. So one way to think about B in the context of predicting the price of a house is, what is a house that has no bedrooms and maybe no square footage and has no bathrooms in it? What type of house might that be? Well, maybe that's a lot. What is the price of the lot? So you can think of B in the intercept in terms of this problem as the price of the lot. So price of the house is equal to a parameter, or a learned parameter, a value, a numerical number that the model has learned that it uses to multiply times the value of a feature for a given observation plus our intercept in order to create an output that is our target variable. Okay. This is a lot. I know we're going to keep going, but we will ground in this a little stronger as we talk about linear regression. I think this is my last slide before that. Let me just double check here. Yep. Okay, so we'll come back to that. So we talked about, okay, y equals mx plus b. We created our first model. Great. Its output price of a house is equal to some trained parameter weight times the number of bedrooms in a house plus the price of the lot. How does a model do that? How does a model actually decide, yep, it's $10,000 is what you multiply by number of bedrooms? How does it know what to multiply by each of these observations, each of these feature observations that we're handing to it? Models, there's a process called model training, and that's what we're going to learn about. We're going to learn about this applied to linear regression, simple linear regression first, which is essentially y equals mx plus b. And these models are trained on data through algorithms to adjust these parameters. So we have one way of thinking about this is that we have we just assign random numbers to these parameters. We just pick a random number for to multiply number of bedrooms by. And then we have a way of assessing how good that was. We basically give it historical data, ask it to make predictions on it, and we measure the delta. What's the difference between how well the model predicted on that versus not? And then we change the weights. And then we see when it gets better and we see when it gets worse. And this picture I have here is basically if we trained a model over every potential combination of parameters, parameter values. Here we have parameter 1 and we have parameter 2. And let's say this is the performance of the model. You can see that for different combinations of parameter values, the model will perform better or the model will perform worse. And essentially we want to have this, in the case of this would be like gradient ascent. And in this case, we want to have the best performing model. So our goal is to kind of find this peak value where our model performs very well because of on the parameters that it has assigned mathematically to that. So this process is called training. So we have training where we give it historical data with answers, and iteratively through many loops, we have it try different values for those parameters. And as that improves, we want to pick the one with the highest performance. That's essentially what we're going to do in training. So let's talk about, do a time check here, linear regression. Yeah, I am going to introduce, let me see, because I want to give you guys another 10-minute break here. Trying to decide how far I go into this. Okay, we're gonna go to, we're gonna go 5 slides in. Okay. In linear regression, coming back to the y equals mx plus b, we're going to learn about a very foundational, this is your first machine learning algorithm. This will be on your exam, and you will see this other places, and it is still used substantially in machine learning today. So this is not, it is an old algorithm, and it is a very traditional algorithm, but it is still something that's very commonplace today. And like I said, the foundations really that we're going to build on to get to neural networks. The goal behind linear regression, what does linear regression mean? We just want to create this line. This line is our predictions. And we want to find the best fit line, otherwise known as a linear function, y equals f of x, to explain the data. So we have all these data points here, and we want to find the line that if you gave me some new x variables, I could predict y. If you gave me new x variables and I predicted y, I would always predict along this red line here. That's what our model is. Our model is this red line. So we want to find the best fit line that kind of averages all these data points in the data. The way that we do that is through linear regression. It is a supervised learning algorithm. So remember, we have unsupervised and supervised. It's a supervised learning algorithm that models the relationship between a dependent and one or more independent variables. So the formula here, the equation for a simple linear regression, simple just means when we only have one parameter. So here in this picture, we only have one parameter because it's y and it's x. You don't have y, x, z, and more dimensions to this. It's just two, an outcome and one input variable. So that's called simple linear regression. So here is our equation for simple linear regression, where y is the predicted output. Okay, from our y, we're going to start changing our nomenclature here. From our y predicted output, y did not change. Y is still y. But notice here we have this, let's start here. Notice here we have this, what's called beta. This fancy looking b here is called a beta. And this 1 here means it's beta beta sub 1. So beta with a subscript 1. Beta sub 1 is our coefficient or our slope. So this is our m. So now I'm no longer going to call it y equals mx plus b. I'm going to call it y equals beta sub 1x. So this is beta sub 1x. X is our input feature. That didn't change. It's still our, x is still our, how many bedrooms are in your house? Do you have 1 or 7? And beta sub 1 is still the value that we're multiplying that by, say 10,000. So beta sub 1 is still our coefficient or our weight or our parameter, but we're going to call it beta sub 1. Notice here we also have a beta sub naught. So when you see the 0, that means sub naught. So this is our beta sub naught, and that is our intercept. So instead of having y equals mx plus b, now you have y equals beta sub naught plus beta sub 1 times x. And notice that they swapped positions. So the b was at the end before, and now the b is in the beginning. So the intercept is the first thing now. And then we introduce the first coefficient times our input feature. Here in some formulas, I'm just putting this here for your awareness. I will drop this in as in subsequent things. But as you read some books and you consume, like if you're reading Introduction to Statistical Learning or anything like that, you might see this epsilon value. This little tiny e is epsilon. It's actually an error term is what it is. And so it represents the randomness that exists in the world. And the fact that we can't truly have a perfect model without actually being able to predict the randomness of the world. But we don't need to dive into that. And I'll probably drop that in subsequent things. But I didn't want you guys to get confused if you saw that somewhere else as you were continuing to do your self-learning and your research. That E is an error term or the randomness of the world. And we will not consider that in the future. So that'll get dropped off. But now, okay, we're grounded in this nomenclature. Simple linear regression, y equals beta sub naught plus beta sub 1 times x. Let's apply this to, let's map this out here on a visual. One question, let's make a model. And this model is going to predict your salary based only on your experience. So you tell me how long you've been in the field or in your industry or how long you've been working. And I'm going to try to predict how much money you make. And so Y here is the salary. And so salary is our Y. So salary is equal to beta sub naught plus beta sub 1 times experience. So beta sub naught is our intercept. This is the value that we're going to predict if you tell me that your experience is 0. So 0, experience is 0 times anything will always be 0. So here in this, on this axis, this beta sub naught is our intercept. You tell me your experience is 0, and this is what I predict. In this case, we said beta sub naught is $30,000. So you make, you have 0 experience. That's your baseline. These stars are all historical observations. People have told me, look, this is my experience and this is my salary. And so I have both pieces of information. I have both experience and I have salaries. What I want to train a model to do is to create a best fit line here, such that if people give me their, people give me a new individual and they tell me their experience, I can make a prediction on what their salary is. So if they tell me, hey, I have, 10 years of experience, I can say $30,000 plus whatever the value is for my beta sub 1 times that 10 years of experience to get the outcome here. Is this resonating with you guys so far? Okay, great. So I'm going to take it one step further here. Obviously, just your experience is probably not sufficient to have a good model because people make different levels of money in different industries, in different job titles. And so if you told me more information about you, I could probably add more features to this model. Instead of just having beta sub 1 times experience, I could do beta sub plus beta sub 2 times industry. What is the industry that you are working in? Are you working in the tech industry? Are you working in education? There's different salary outcomes associated with that. And then I could maybe add another feature here and say plus, I'm trying to think of another truly salient region. So what area of the country do you live in? Do you live in New York? Do you live in South Dakota? There are different standards of income, different living expenses associated with each of those areas. So we could do plus beta sub 2 times, where your location is, where your home base is. So if we could add more information to this model, how would we write a more generalized formula to encompass that? If this, I wish this is one of those things where I wish I had a whiteboard. Let me see if I can actually draw this. So how do we write a more generalized, we started y equals, how do I erase that? I'm going to move this m. So we started y equals mx plus b. I'm actually going to put it b plus mx just to, and we evolved our formula to be y equals beta sub naught plus beta sub 1 times x. And what I'm suggesting is, what if we continue to expand this? And we said beta sub naught plus, sorry, that's supposed to be a 1 there, beta sub 1 times x sub 1 plus beta sub 2 times x sub 2 plus beta sub 3 times x sub 3. We can get a better model by adding more information to it. So this, let me change my color here. This is called simple linear regression. And this one here is simply called linear regression. I'm just going to do LR. It's easier for me. Okay, so this one here, this full expansive formula, and by the way, you can keep going, and you might actually see it written as beta sub n times x sub n. So you can keep going for however many features that you have. If you are a math nerd, you're going to like that notation. And to further, what they like to do with math sometimes is really simplify formulas and make them like really condense their representation. So this is a condensed representation of that formula. And what it's saying is, it's saying, okay, y, you might see this is called a hat. This is called y hat. We have y hat is what we're trying to, is our, remember I said that all models are wrong and they're oversimplification. So in theory, y is like the perfect model. So let me get a slightly different color. So y is like a perfect model. So y is like what we're trying to get to. It would be like 100% accuracy. This is like the theoretical model that exists that we could aspire to if we had everything that we needed to do. Y hat is our model. Later in this, you might also see y is also used as like true outcomes. But just so you know, so y hat. So the way they wrote this formula, is y hat is equal to beta hat sub naught, so just all of our trained weights for our model. So this is our intercept here. And then it's the sum, because these are just sums. We're just adding each of these things together. So they just generalized this section of the formula and said that it is equal to the sum starting at 1, where 1 is the first feature that we have across all of the features. So this is how many features do we have? Across all of the features, you're going to take that feature times its coefficient value. So x sub j times b sub j, which is the same thing that we're doing in this formula. So it's just saying multiply for each feature times its coefficient, add them all together, then add the coefficient, then add the intercept in there, and that's the formula. So this is just an oversimplified formula. You don't need to particularly know this. The only reason I put this out here is so that you guys are aware. It's an awareness thing. So as you're reading things online, if you see this representation, you know that it's the same thing. So this is equal to this here. They're the same thing. And this is just a shorter formula of this one down here. So just an awareness thing. The one more awareness thing, and by the way, we will primarily use this this one here, the fully written out one, just for clarity in this class. But in neural networks, sometimes you will see it condensed even more. People like to really shorten things. So in neural networks, you might see it simply represented as this. So all of this information here just represented as y equals x times the coefficient, where x in this case is actually a matrix representation. So we're going to get a little deep here, so forgive me, and then we'll come back up for air. When you start working with neural networks, you can write all of the input samples as a single matrix. So think of your Excel sheet here where you've got your columns and your rows, where this is like column 1 and this is row 1. So this is column 1 here, maybe row 1. Oops, sorry, that was supposed to be maybe row 1. So it's like column 1, row 1 observation. And you can go ... all the way over to, row 1. I think I mixed those two things up, but you get the idea. Row 1, column n observation. So you can put all of your, it's kind of like an Excel sheet, you can put them all into a matrix. And in math, you can represent this matrix as just x. It's one value. And then you can apply mathematical linear algebra operations to it. And that's how neural networks work. So in this previous formula where we said y equals x, giant X, big X, matrices are always represented as big X's. So when we say y equals big X times beta, this is actually a linear algebra operation. And what we're doing is we're taking this beta coefficient times this entire matrix. We're taking this, where this beta is actually a vector of values, 0.1, 0.2, whatever, 0.8. Those are our trained weights, our coefficients, and you can actually take these trained coefficients and multiply it by this matrix to get the output. So it's a very simplified representation. All of this founded in just our y equals mx plus b, which I think is kind of cool. But that's as deep as we'll get for neural networks and linear algebra. I just wanted you guys to have all that context so that as you see these different formulas, you know that they're just all the same thing. They're all saying the same thing, they're just different representations. All right, that was my last slide before our break. Let's take a 10-minute break. And when we come back, we're gonna talk about simple we're going to talk about simple linear regression. And we're going to talk about, so just the basic, the y equals mx plus b with one feature. And we're going to talk about how do we actually learn those parameters? How do we learn 10,000 is the number that we multiply by a house? So that's what we're going to talk about when we get back. 10 minutes. I'll see you guys at 2:17. I apologize. I am back here. Okay. Simple linear regression. So 40 minutes left here. Let me see. I think we'll be able to get through. Yeah, I think we'll be able to get through these slides. Okay. So for now, we talked about how we can have lots of features. Let's just bring it back down to one feature. Let's imagine we have one input and one output. So one dependent Y variable that we're trying to predict, such as house price, and one input variable, such as number of bedrooms. We're just trying to predict house price based off of number of bedrooms, or we're just trying to predict salary based off of experience. We want to fit the points on our XY coordinate with a line, and that line is going to be our model. So we want to train a model. How do we know which line we should use? How do we know that if we we have X and Y here, and X is our experience, remember, and this is X, and Y is our salary, what we're trying to predict, and we have some historical data here of some individuals with experience and salary. How do we know that this line or this line is better? How do we know which one to choose, or which one is better than the other? How can we quantify and measure that? One thing we can do in machine learning is create something called an objective function. This is a generalized term. We're going to make an objective function that tells our model, this is how you decide that you are a good model. This is how we quantify that this is a good model. For simple linear regression, we're going to use something called the sum of squares error, the SSE. And this is essentially, what did we predict versus what was the actual outcome? And let's add all of that together. So in this case here, I should have done those lines in a different color because that is confusing. And I actually don't want to use red. I will use blue. So I'm going to try to do these lines in blue instead. Sorry, they're not supposed to be squiggly. They are supposed to be straight. What we predicted is this line. So for this X, what we predicted is here, and where the X is here. So, oh, good. We did very good there. So what we predicted was, let's say, 40K, and what the outcome was actually 40K. So what we predicted, the predicted is Y hat, minus the outcome is Y. And in this case, this was 0. And this is called a residual. This is called a residual. Y hat minus Y is a residual, otherwise known as an error. This is the error. How incorrect were we? From what we predicted 40K. Now let's look at this one here, this data point here. Let's imagine that's 50K. And this model said, let's imagine that's 55K. 55. The actual outcome was 55. And M1, let's call this M1. M1 said 50. So 50 minus 55 is -5, was our residual here. And that is the delta between this point and here. If we want to measure the delta between this point and here, let's say this model said 40. So M2, let's call this M2, actually said 40 minus 55. So -15. So on this data point particularly, M1 performed better than M2. Because the residual or the error for this data point was smaller. Now, what if we calculated the error for all of the data points? And then what if we added them all together? That is the sum of, that's the sum of the residuals, the sum of the squared error. Okay, so for this 2D problem, again, this is our formula that we're working with. Y equals beta sub naught plus beta sub 1 times x sub 1. Just one feature here. To find, if for you math nerds here, how do we actually do that mathematically? Everything that we said on the slide mathematically. How do we, instead of just applying trial and error and trying a bunch of different lines and seeing which one works, how do we actually use math to create a formula? And if you guys remember from high school algebra, you set the formula equal to 0 and you solve for it. And then when you set it equal to 0 and solve for it, you can actually find the missing variables, the values for those missing variables that solves that formula. You will not be tested on this, but I wanted to give you this piece of information that the way that works is to find the values for these coefficients. We would minimize this objective function. So we would take the derivatives of our sum of squared errors, our SSE. We're going to take the derivatives of sum of squared errors with respect to the coefficients. We set that to 0 and we solve. That is the way that linear regression actually finds what those optimal weights are for a best fit line. Feel free to dig in more if you are interested in really understanding that. You won't be tested on applying a partial derivative to the objective function with respect to the coefficient, setting it to 0 and solving it. But I do want you to be able to understand conceptually how this works. So let's go through this. I want you to understand how this best fit line gets evaluated and chosen, because this is the concept that generalizes to all machine learning models. So how do we measure the correctness of a line? Like we have a regression best fit line. How do we know how correct or incorrect that line is? How do we know how good it is compared to other lines that we might draw? Well, we have our y hat. Y hat is sometimes represented with a tick in some presentations because it's a little easier to put over a y than a hat on the keyboard. So y hat here is what we predicted. So this is y hat. Y hat is always on this line. This line is always the outcome of our model. And here's where the true outcome was. The true outcome was up here. So the residual error is the difference between the true outcome and what our model predicted. One thing I want you to note here with simple linear regression, is that it will always be a straight line. Okay, it will always be a straight line. You will never see our line go like this. We cannot do that with simple linear regression by the constraints of the formula. The formula that we have that says y equals beta sub naught plus beta sub 1 times x sub 1 plus, that will always create a straight line. It can't create something dynamic like that. The reason that I say that, there we are, is because this model will always have a degree of incorrectness. Remember when I said that models are an oversimplification of the real world? If this real world is all of these data points here, the model is, of course, this straight line here is, of course, an oversimplification of that. Whether we put the line here or here or here or here, of course, it will always be wrong. It's never going to be correct for all of the data points that we have collected. And we don't really particularly want it to be, but I just wanted to emphasize a connection there between what we had said in the beginning about all models are wrong. This model will always have a degree of wrongness by constraints of the formula. There is nothing that we can do to make the linear regression actually be correct for every data point in our training set. So let's measure the wrongness. Let's find the model that is the least wrong on average. And to do that, we're going to calculate this residual error, and we're going to add it up for all of our points. So we're going to calculate it there. We're going to find the error here. We're going to find the error here. here, 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 and here. And we're going to add all of these values together. So if this was 2 and this was 3, these are just points on a graph, so we can find the distance between them, this point and this point, using a distance metric between 2 points. You can use like Euclidean distance, or you can find the different distance here. So this is 2. We're going to add all of these values together. So we're going to sum y minus y hat, and we're going to divide it by n, how many observations we have. That's going to give us something called the mean squared error, the average squared error. So in this case, we're squaring it. We're going to sum those two together, square that value, divide by n. So that's the mean squared error, the average squared error. Our mean squared error measures the average difference between the actual and the predicted values. So one natural way to measure how well a line is, how good a fit is on average, how incorrect were we? On average, how off were we from predicting the house price? That way we can create a line, and we can look at all of our data points, all of our training points, all of our historical points, and we can say, well, on average, we were off by $12,000 on our house predictions. And we calculate that by adding up for each observation how incorrect we are, taking the square of that, and then dividing by n. When we do 1 over n, this is just the same thing as dividing by n. So we have a summation function out here. This is just the generalized representation of that. Does anybody know, why are we squaring this? Why might we square the residuals? Okay, think about that for a second. We're going to walk through an actual example here, and to ground this a little more. And if I don't answer it by the end of slide 24, then I will come back to that. Okay, we have the high level concept. Let's start to dive in a little deeper. We're going to break this down by first looking at sum of squared errors. So let's look at the sum of squared errors. We're talking about mean squared error, where we took the difference between everything and we squared it, and then we divided it by n. Let's just, for 1 second, let's not divide by n. Let's just take that out, and let's calculate the sum of squared errors for a particular problem. So let's do the SSE. The MSE is just an average of the SSE. But for a second, for these next couple of slides, erase that. So when I save the annotation, that doesn't confuse somebody. Okay. So let's look at the sum of squared errors and linear regression here. We have these data points, and we want to draw a line that is the best fit. Okay, let's put a line on here. We have this line that goes through these 2 data points. Let's calculate the sum of squared errors. Well, this data point is on the line. This data point is on the line. And this data point is a distance of 7 away. So our sum of squared errors would be 7 squared. Okay. Now we have 2 lines. We drew a different line. We drew a red line here, and the red line goes through these 2 points. The distance between this point to this line is 5. The distance from this point to this line is 7. Which line has a lower sum of squared errors? Because we want to minimize error. We want to minimize the sum of squared errors. We want it to be as close to 0 as possible. Is the red line or the orange line better? Are these colors distinct enough? Do you guys know which one's orange, which one's red? They're kind of close to each other. So this orange line, these data points, each of these data points are our training points in our data set. And we want to know which of these lines is better. Does anybody have a guess? 50-50 chance here. Red or orange?
I would say red.
The red line. Why would you choose red?
Because I read that Luke and Josh put red, so I'm going with it.
Oh yeah, there. I didn't even see the chat here. There we go. Luke and Josh. Yep, red. Sorry guys, I didn't have that chat open. The red line. Where would you say red, Luke and Josh?
I guess it seemed like it was less far off. I guess I was just assuming that 5 less than 7.
Yeah, that's a good assumption. So red line is 5. 5 is the error from this point to the red line. And so this is going to be 5 squared. And the 7 is the error from this point to the orange line. So this is going to be 7 squared. And since 5 is less than 7, we don't even need to evaluate the squares. 5 is less than 7, so that's going to have a lower error. Okay. We put a new line in there that's a little garish and hard to see, but a very, very neon yellow line here. Now which line is better? I'm going to do red, S. Red, yellow, or orange. And we remember our red and our orange didn't change. So red is 5 squared, which is, what's 5 squared, guys?
25.
Show me.
What is 7 squared?
49.
And how do we calculate the error, the sum of squared error for the yellow line?
Is there a difference that the yellow line has a 3 on the side and on top versus the 5 on side?
So we have, technically, I was oversimplifying the red and the orange. What we're really doing for the orange is we're saying 0 plus 0 plus 7 squared is equal to 49. And for the red, we were actually saying 0 plus 0 plus 5 squared is equal to 25. Because these points ran through the line, so our error was actually 0. In yellow, we still have a point that the error is 0, so it's still 0 for one of them. But yes, the other 2 3s, we need to take account. I think Josh has got it here. 3 plus 3 squared.
I, 36.
36, yeah. I think, Josh, we need to add them first and then square it. 36, which is, 36 is, I think, did I do that correctly? Hold on. So our best fit line, according to this, I think we do add them first and then square it. Our best fit line, according to this, is actually the red line here. And this is something that I don't know about you guys, but I wouldn't have easily been able to do by just looking at it. I wouldn't, without the numbers on the screen, I wouldn't have been able to look at the red line, the orange line, and the yellow line and easily say, yep, it's definitely the red line. And that's what these models do for us. They offer structure, mathematical formulas, and frameworks for us to actually make data-driven decisions, data-driven decision making. Yeah, I would have guessed the yellow line too, Luke. That would have been my guess. But actually, the red line is better. So these models help us overcome our human bias at time by supporting with these data-driven decisions, data-driven outcomes. So hopefully that helps you guys understand how we actually assess what these models are.
Actually, can we back up for a second? I got a question.
Yeah.
Why don't we use both the 5 and the 7 on the red? Or, you know what I mean?
I do know what you mean. This is like a bad picture at times. Let me see if I can clarify here. Let me erase. I think I shouldn't have made this red there. There we are. Let me try to color those in some like brighter blue colors here. These are our data points. So this data point is at some coordinate, like 1, 1. And this data point is at some coordinate, like 5. Oh, I don't want to use value 5 because that's confusing. I'm going to use something else. 4, 8. Okay. And this is at some value, like let's say 10, 2. Okay, where this is x, so these are xy pairs. When I say 10, 2, I'm giving you the x coordinate and then the y coordinate. So this red model, the red model makes predictions along this line here. So when you give it an x value of 1, when you say it, hey, what's the x value of 1? Tell me your y. What do you predict? It predicts 1. It says 1 is the outcome. When you give this red model an x value of 4, when you say, hey, that's supposed to be a 4. This is my 4 value. Predict an outcome for me. It says, let's see, I got to do this correctly. X, what did I say? This was 4, 8, 8 minus 5 is 3. Apparently this is 3, so that can't be 2. But whatever, you get the idea. So apparently this is 3. It says, when you say, what is my y? It says 3. So that point there, this outcome here is 4, 3. When you give the model a 10, this actually can't be 2. That has to be higher than 2. So I'm going to make it a 4. Just doesn't work in the representation. When you give the model a 10 as an x value, and you say, hey, red line model red, what do you predict for 10? It says 4. 4 is the outcome. The orange model makes predictions in a different way. When you give the orange model an x value of 1, it also produces 1. When it says y, it actually says 1 as well. And when you give the orange model of 4, it predicts the outcome as A, or as 8. When you say, I give you a 4, what's the outcome? It says 8. And when you give it a 10, x is equal to 10, the orange model predicts the outcome maybe to be 10. So the reason that so in this case, the red model here, let me switch back to my orange purple color. The red model here is correct in this one. What it predicted are y hat minus y is equal to 0 for the orange model, and actually the orange and the red model as well. They were actually both correct. The red model here, when we handed it a 4, it said 3. It said 3. Well, our ground truth answer, our data point here with a 4 is actually an 8. So we have to say that 8 minus 3 is equal to 5. And that's where this 5 comes from. It's the error, it's the difference between this value and this value. In this spot here, our model, we gave it a 10 and it said 4. It was actually correct because of this data point, because this data point is at 10, 4. So in the red model, that's why I oversimplified. I should have written the whole formula, so I apologize. The entire formula for the red model, red would have been equal to the first data point. So it's y hat minus y. So we predicted 1 and it was 1. So it's 1 minus 1 plus we predicted in this red model 3, but it was actually 5. I'm going to simplify this by actually doing 8 minus 3 instead of 3 minus 8, but 8 minus 3 plus 10 minus 10. Which is equal to 0 plus 5 plus 0, which is equal to 5. And then remember, we're squaring these. This all should have been squared. Okay. Did that add clarity as to why we use the 5 in the red model and not the 7?
Maybe not, because the 8 minus 3 and then the 10 minus 5 leaves 5 of 5.
Oh, I'm so sorry. You are correct. I have a typo there. I don't know where my head was. 10 minus 10. I'm sorry.
Oh,
this 10 and
Yeah. That
and
makes
this
sense.
10. I apologize. This 10 and this 10. Or no. That's when we give it 10. There we are. That 10 and sorry. This should be 4. When we give it 10, it's predicting 4, and it was actually at 4. 4 minus 4. I'm sorry. I made that very confusing. Sorry, these are the y outcomes. The y outcomes. So we are not looking at the x's. I have the wrong thing underlined here. Y outcomes. So x, y coordinates, we're always looking at the y. So we're looking at the y outcomes when we're evaluating the model. So this is 4. This one up here is 10. That's the 10 I got mixed up with. This is when we give it 10, it's predicting 10. I just mixed up with that 10 there. But that would be penalization. So it's off by 7 for the orange model. Okay, well, we'll sit with that for a second. Let me see if I said there was something I was going to come back to if I didn't get to it.
Y and squared.
Oh, yeah, thank you. I'm trying to think of which slide to do it on here. This one's fine. Why do we square this? Any thoughts on why we might square this now that we have maybe a little deeper understanding?
Does it remove the negative thing?
That's exactly it. So technically, let's not square this for a second and see what happens here. What if this is positive 2? So if we take y, let's just say we're doing let's say we're doing y minus y hat, and we have to do it in a consistent way, right? We can't sometimes do y minus y hat and then other times y hat minus y. We have to do it the same way. So we're going to do y minus y hat. So this is 2. Oh, I did not mean to zoom in. That's interesting. Now I know how to do that. This is 2. This is 3. This is actually -2 because it's below the line. So it's going to be a negative value. This is +2. Let's play with me here. Let's do -3. I'm trying to do something clever here. Let's do -2 here. And let's just say these two are -1. And let's say this is -2 and this is -2. And this is this is +3. Sorry, these are not negative. I'm trying to do two things at once here. These are all positive. It's negative if it's below the line. Let me add one more point in here because I'm trying to make a point here. And this point will be -6. Okay. I think that's right. I think I did that correctly. So let's add all these numbers up together. So we're gonna have let's do the positive numbers first, and then let's add up the negative numbers because it's going to be easier for me to know if I got this correctly, did this correctly. So let's add up the positive numbers. So 3 plus 2 is 5, plus 2 is 7, 8, 9. Oh, look, somebody did that for me. 14. Thank you. So we have 14. Let's add up the negative numbers. We have 6 plus 4 is 10. And 3 is 13, 15. So I was off by 1. Let's change this to a -5. There we go. Negative numbers are 14. So technically, if we added all these together, if we did 3 plus -2 plus 2 plus -5 plus 2 plus -2 plus 1, etc., at the end, what happens? What happens to our error? What is our error? There we go. Thanks, Luke. Our error is 0, which 0, an error of 0 implies a perfect model. It implies a perfect fit, a perfect line that's correct all the time. And this line is not a perfect line. It is not a perfect fit. It is not correct all the time. And so this is we can't just add all the numbers together if there's negatives in there, because the negatives will cancel out the positives. The negative error and the error that is below the line and error above the line will cancel it out. And in reality, if we think about this conceptually, an error of +2 and an error of -2, if we think about house prices, they are equally incorrect. So if you are under-predict the house price by $2, if you over-predict the house price by $2, you are still off by 2. It doesn't matter in the context of our problem whether it's a negative number or a positive number. So in order to get around that, we just use clever math. And this clever math is to square the number. So we're going to square the number, and that will remove the negative sign, and that will treat both residuals, positive and negative residuals, equally. And then we divide by n to get the average. So that's information for you on just, you want to be careful, make sure you don't just add all your residuals together and when there's negatives in there and not square. So that's why the square is there. In the next class, when I say next class, in the next machine learning course, when we talk about metrics and evaluation, we'll dive more into this. So we will do more on metrics, and we will look at clever ways to get rid of those negative signs and all the different representations and formulations of the problem. So this is kind of, there's your precursor to the next class. For this class, I just want you to conceptually understand how we know one line is better than the other. I want you to just conceptually understand that we have formulas for understanding how to quantify that one line is better than the other. A couple of assumptions to be aware of. So linear regression is, sorry, I'm just trying to do a time check here. My phone, there it is. All right, we have a couple of minutes. Let me see how many slides we have left here. I think we're okay. We're just, yeah, we might go a little bit over, but we really are just a few minutes left here. We covered 90% of the content. So a couple of things I just want you to be aware of as you are learning more about linear regression on the internet. You might see these things called assumptions. And assumptions are things that we have to make sure that they are true about our data set prior to applying linear regression. So machine learning used to be founded, and still is founded, in statistics, really heavy statistics. And in statistics, sometimes they have all these assumptions that you have to say, well, your observations must be independent of each other. Independence means that the observations are correlated to each other. I'll give you an example of independence. You work for a company and they are making phone call surveys to houses in order to collect what people are going to vote for in the election. What's your vote going to be in the election? Well, because they want to try to predict the election outcome, you know, all these forecasts of who's going to win. And it is independent if you make random phone calls to different houses. However, you violate independence if you make a phone call to the same house, because those observations are related to each other. Those two people live together. There is correlation. They are correlated in terms of the fact that they're more likely to vote similarly to each other because they're influencing each other. So that's not something called an independent sample. If you're making phone calls and they're people of the same household, they live together. So your observations must be independent of each other. They can't influence each other, essentially. So there are a whole set of observations like this. And in traditional statistics, we really grounded in these and said, and had rules and would throw out data sets that didn't meet these. The field has evolved. Where I'm getting to is now in the field today, a lot of times we just throw data at the problem and we don't even look at these assumptions. That could be good or bad, but we just focus on the performance of the model and having better outcomes. So I'm not going to focus on assumptions for this class. We're not going to talk about normality or multicollinearity. However, I did want to put these out there because as you guys are reading about linear regression, you're probably going to see these things come up. I wanted you to be aware of them, encourage you to understand them and what they are. But we're learning linear regression so that we can learn logistic regression, so that we can learn activation functions and nodes within neural networks. So this is a stepping stone to get us there. So I'm not gonna put a lot of emphasis on assumptions, but they do exist. It's kind of worth reading about, at least understanding them. We talked about the two types of linear regression. Simple linear regression is just that one independent variable, y equals mx plus b, where you only have one variable. Multiple linear regression is where we have all of the variables. I'm no longer going to make a distinction. I'm just going to say linear regression from now on. So we're just going to say linear regression. There could be one, there could be multiple. This is the entire formula here. When we say multiple linear regression, when I say more than one variable, this is what I mean here. You guys saw me write that out. 1 equals beta sub naught, beta sub 1, beta sub x sub 1 plus beta sub 2, x sub 2 plus all the way up to beta sub n, x sub n. This is the formula that I will use for linear regression. When I talk about linear regression, I'll write it in this formula. Last slide here. last two slides here. A few limitations on linear regression that you might have already picked up on. It's not always a good choice. And when is it not a good choice? So this box here, probably a good choice. These points seem to have a linear relationship, experience and salary. This here is a non-linear relationship. There's something interesting going on here. Probably not a good fit for linear regression, because linear regression is only going to make a straight line here. And no matter what we do, no matter how we turn that line, we're not going to be able to create a good fit, a good line for this relationship. Linear regression is very sensitive to outliers. So we had one outlier up here, and it's very clear looking at this picture that the better line is obviously here, but that one outlier pulled our entire line up and increased the average error across all of our other data points. Not a great fit for outliers. Also, not a great fit for this type of data representation. No matter how we draw the line, we're never really going to have a good fit on this data. So looking at your data can help you understand if linear regression is a good fit or a bad fit. So in summary, this algorithm, linear regression, it's going to be sensitive to outliers. It does assume linearity. So this is a linear assumption. So these are these situations, well, this one is linear, but it's just sensitive to outliers. This is a nonlinear relationship. This is a nonlinear relationship. So it does assume linearity. It does assume constant variance of the residuals. And it's not really suitable for modeling more complex relationships. So we're going to explore other algorithms that are better suited for complex relationships. Okay, that is it for today. I'm going to stop screen and I'm going to end the stream and I'm going to ask if there are any questions.